All right, so everybody back. Let me just first say at the outset, we spent a month in part, what, should I go? Yeah. We spent a month in part because the assumption was we screwed up, and so half of that time was, no, we didn't screw up, we did it right. I just also want to point out in interpreting these plots, this is data for March. It's a March average. It's at 1 p.m. local time. This is also for March. This is an average, I think, of 2 years. I can't read the 2008, 2009. This is just for an average of March 2009. So it's pretty one-to-one. We did not screw up. We did the right thing. Does anybody have any suggestions as where we should look to try and understand why the model fell apart? Like, what diagnostic might we want to look at? And the clue is in the stuff we talked about in the first lecture. And I don't hear, my hearing is terrible, so if you have an idea, you have to scream it. That's close. That now, as it turns out, the KZZ for these two calculations is the same, but it's related to that. Okay? So the first thing to look at, based on our discussion, is neutral composition. What happened to our atomic oxygen and molecular nitrogen between the two simulations? Did we do something? And the answer is yes. So here's hours of the beginning of the calculation, 700 hours. I don't know, it must be like a month or something. And here's, it's a column integrated, but it's essentially a measure of O to N2. The top curve, and this varies, I guess, like a diurnal variation or something. The top curve shows it's basically constant. So at the end of the month, you're oscillating around 0.7, all right, in the idealized case. Our new realistic run, after about 5 days, it went down to a new equilibrium. And you see this equilibrium is much more variable because there's real weather in there, but it's definitely a different space than the idealized run. So something we did changed the neutral composition. So at least our ionospheric response is consistent with our neutrals. So at least that much is correct. So now the question is, what changed the neutral composition? The suggestion was KZZ. Now, as I say, it's constant between the two. The key thing to remember is that with these realistic models, you're resolving other things that are historically bound up in this old 1D KZZ parameterization. So what we looked to next was the vertical wind. And we took spectra of the vertical wind at the equator. And on the right is the old standard input wave number for either diurnal cycle, a semidiurnal cycle, terdiurnal cycle. And on the left is the vertical wind spectrum for the case with the realistic meteorology driven by no gaps. And the standard NCAR was using an idealized tidal model, which just has 2 cycles. Once per day, twice per day. You see on the left, there's a very rich spectrum. Oh, and the other thing is that the once per day is going as a wave number 1, so it's 1 sine wave across a latitude circle. It's traveling westward with the sun. That's called a migrating tide. The ones that go with negative wave number are going the opposite sense. They're called non-migrating tides. We'll talk more about that shortly. So you see that the vertical wind spectrum from the realistic case is a very rich spectrum. There's a lot more going on. We have just greater upwelling. So KZZ aside, we have something else going on that's pulling molecular rich air up into the thermosphere and flushing the atomic oxygen out. So you can't use the same KZZ because now we're resolving more with the realistic weather model, okay? And that's, so to compensate, we have to change the KZZ and we have to lower it, all right? This is, I don't know if you can see all the plots, but what I'm trying to show is a number of model runs with different colors as a function of, the NCAR guys like to use these log pressure levels, and there's altitude scales on the right. This is roughly the 110 kilometer region, and the point is that the old models, the O was too low. When we went to the case, the only case where we used the realistic meteorology and the KZZ, which was lower than the idealized case, we got this red curve, and this is some observations from SABRE. And it's not great, but this curve's the only one that even comes close to getting the mesopause atomic oxygen correct. You look at the O to N2, you'll see that this red curve is different than, actually this curve brings us back to the default case. So rich meteorology, low KZZ, brings us back to the high KZZ limited meteorology case. So the black and the red are supposed to be the same. And if you go down there, you see that our ionosphere, I'm going to have to go over my canvas, is now out towards about 7 times 10 to the 5 instead of, and there's a, I think these mean curves don't show up, instead of about 5 or 6 times 10 to the 5. This is now at 340 kilometers. So again, the bottom boundary at 95 kilometers changed the F2 peak 250 kilometers higher. So it's a real, I think, a good demonstration. And since the bottom boundary, this KZZ, is all sorts of meteorology, which we'll discuss, bound up in it, it's a good example of sort of this lower to upper atmospheric coupling. So we had our original standard NCAR, we had the bad model, we have the improved model. It's maybe not as great, but we do a lot better. And you're beginning to see that we're still beginning to resolve some of this, the two ionospheric arcs in the improved model, which we were not doing at all in the bad model. Okay, so the summary is that including the more realistic meteorology obviates the need for a ad hoc high KZZ value, which again, this is something that people have been playing with for 50 years. So now for the rest of the talk, we're going to talk about what is more realistic meteorology, what exactly is in there. I mentioned something about tides. That's one class. Planetary scale waves, large waves, gravity waves, small buoyancy waves. We'll talk about all three. I do want to just mention some of the structure of the Earth's ionosphere, which I know you've talked about, why there are the two separate stripes centered around the magnetic equator. I always like to show this picture because it's an NRL camera that was placed on the moon by the Apollo 16 astronauts, and it's a measure of, it's the far ultraviolet airglow, and it's a measure of the recombination of O+. And I think you've seen a version of this slide before showing how an electric field can be generated from collisions between ion and neutrals in the lower thermosphere, the E region of the ionosphere. That can cause a drift in the presence of a perpendicular magnetic field. And then at high altitudes, you have diffusion down along the field lines, and you have the recombination. So this recombination releases the airglow that they saw on the lunar camera. And you see it's about 20 north or south in magnetic latitude away from the equator. So that's what the two stripes are. When I was looking at vertical wind, I was looking here, but you see that this is coupled to the ionospheric peaks away from the equator. And this doesn't happen at all on Mars or Venus because Mars and Venus don't really have a magnetosphere. And this is supposed to be an artist's conception of the magnetic fields or the interaction of planetary atmospheres with the solar wind, Earth, Venus, Mars. And so you might say at first glance, like Mars is singularly unexciting. It's just this little ball of rock with the solar wind blasting past it, whereas the Earth has got all this complicated magnetospheric physics. Now, this is why the question of planetary escape is interesting for Mars, because the fact that the solar wind can gain access to the Martian upper atmosphere is thought to be one mechanism for stripping off gas from the Martian atmosphere. And so that's one of the things Maven's going to look at. Now, it also turns out, if you look in a little more detail, that the Martian crust is partially magnetized, and that magnetization varies in certain places. And that magnetized crust can create what are called mini-magnetospheres. You see these little closed loops here, and that can actually cause a little bit of resistance to, for example, the solar wind hitting the Martian atmosphere. The cartoon here puts them in the southern hemisphere, and that's accurate because that's where it's more commonly, it's where the magnetism is higher. And satellites that have measured the electron density peak, when this is now latitude, longitude on Mars, this is a measure of magnetic field, crustal magnetic field strength. There's supposed to be some orbital swaths going through here, this peak region. You see this spike in the Martian electron densities, and as we talked about, dissociative recombination is inverse with temperature. So if the electron density spikes up, the thought is that the temperature went up, that the dissociative recombination went down, and so that there's some sort of heating mechanism in these little mini magnetic magnetospheres, and that's something that's going to be looked at by Maven more carefully.
What are the units of that map?
Why what?
The units, in which units is this map?
I'm going to say nanotesla, but you know, I'm not really, I don't have a real sense for what that is compared to like the Earth or something, but it's nanotesla 220.
But that's at some altitude, I think.
Okay.
I think this is, I don't know. I would have thought this was a measure of the.
That's nanotesla at 400 kilometers above the surface.
Okay.
It's 2.5 to 3 orders of magnitude less than what you measure.
Okay. So, as I said, a reason for mentioning, going back and talking about this little sort of electrodynamic stuff, is more recent Airglow images since the lunar observation have shown waves in the Airglow, and this was a paper by Tom Immel et al. And the waves in this Airglow actually was probably the single thing that got the ICON mission funded by NASA. And the ICON mission's objective is to look at these waves, and he shows here there's some dotted lines to link it to oscillations in temperature with the same wave number. Let's see if this, and so the idea is that it's tides. So we're going to look at tides for a little bit. And I don't know if it's which slide it's on, but there is a chapter which isn't referenced in the like the guide to the lectures, but it's in the text from several years ago by Walter Scheid that really goes into this and explains all this in depth. And I'm just sort of going to show some phenomena. He gives you the real derivations and explanations of all this dynamics, and so you should look at that as a good reference. There are tides ultimately are linked to release of heat, and with the rising and setting of the sun. And two are most relevant. There's the absorption of sunlight by water vapor. There's also the latent heat release from tropical convection. And there's the absorption by ozone in the middle atmosphere. And the depth of the absorption, for example, ozone, it's a deeper, thicker absorbing layer, guides the vertical wavelength of the tide that's produced and the mode of propagation. So as I said, there's the migrating tides, and that's from the absorption of ozone, typically giving you a semi-diurnal variation. The water vapor heating giving you more of a diurnal variation. The semi-diurnal one tends to propagate up into the lower thermosphere more readily. And then there's non-migrating tides, which is the latent heat released, But these are locked to specific geographic regions because, you know, we have roughly 3 rainforests on the Earth: Amazon, Africa, Southeast Asia. And so that's sort of a natural wave 3 pattern, and that's thought to be linked to possibly the wave 3 pattern we're seeing in the tides in the lower thermosphere. That picture of the Airglow showed wave 4, but that's an artifact of the sampling. It takes a day to get the samples, and then so you're going to get 4 oscillations in the time it takes to make the samples. These tides grow with amplitude exponentially due to the decreasing background density. So this is just a figure showing an attempt to use, this is not the whack-a-mole atmosphere model, it's a Japanese model called Gaia. And they really tried to take the rainfall pattern, this is in millimeters per day, from the 3 rough regions of convection and link it to temperature oscillations, wind oscillations, and ultimately electron density fluctuations in the thermosphere. They were only partly successful. The thought is that it's probably not so simple as simply this wave 3 just mapping itself onto the lower thermosphere, and that there's interactions between different waves, and it's a lot of, there's some nonlinearity involved. But there's definitely something to this. On Mars, remember I said that a lot of the math is, the Coriolis is the same, the seasons are the same, so a lot of the math is the same for a lot of these wave activities, the wave modes and all that, but the forcing is different, so that's really what distinguishes the two. The absorption by dust, which can be a deep layer in the Martian middle atmosphere, kind of serves the role that ozone does on the Earth. Mars doesn't really have the ozone, this is a little bit of ozone, it doesn't have the ozone layer that Earth does. Earth doesn't have the dust layer that Mars sometimes has. Both of them generate this semi-diurnal oscillation in the lower thermosphere. Then Mars doesn't have the latent heat release, but it does have a very strong diurnal heat cycle in the lower atmosphere, and that superimposed with the very large topography is what drives a non-migrating tides. In other words, they don't follow the sun necessarily, and they have their own wave. I think it's more like a wave 3 pattern in the Martian lower thermosphere. So the aerobraking data show a lot of these oscillations pretty clearly, and there's a fairly rich literature looking at, this is longitude, this is mass density for 4 different altitudes, looking at these, and this is the Mars Global Surveyor data. So they had, again, all these missions come in, and to circularize the orbit, they have an aerobraking period. And so there's a fairly decent literature on decomposing these, the wave modes and trying to link it to the surface forcing on Mars. On the right, you see, again, Mars doesn't have all this electrodynamic variability that the Earth does. What you see is the height of the ionosphere moving up and down. And again, it seems like there's some wave mode linked to that the thought is it's linked to tidal forcing from the lower atmosphere. All right, so that's tides. Wave number 2 are planetary waves, also known as Rossby waves, large scale. I usually think of it for explaining to people like it's the reason the jet stream, varies from north to south as you go around the globe. So it may be, one sine wave, 2 sine waves. In the troposphere, you can get up to about 7. In the middle atmosphere, it's usually 1 or 2. The key thing is that the restoring force here is actually the change in the Coriolis as a function of latitude. And so this, again, is where the rotation serves to generate this variation Coriolis. And you can even see this in spinning tabletop fluids, that if you set the wave, if you have a trace and you generate a wave in a tabletop fluid, the oscillation amplitude will depend upon how quickly it's spinning, because that's the restoring force. Now, the mode of the propagation of these things is to the west. That has to do with conservation of vorticity. Again, okay, so here's the reference to Walterscheid's book. So as a wave is moved to the north, where the Coriolis is greater, to conserve vorticity, it'll spin down a little bit, and so you'll get a circulation, anomaly circulation like this. And then if it's moved to the south, it'll tend to spin up. The combination of the motion here going southward and the motion here going northward will tend to push this wave to the left. And so Rossby waves propagate westward. Now, I don't have a pretty picture of these Rossby waves. But this is a useful plot to see because it's a category plots that you often see when people talk about waves in their models. They're called Hofmöller plots, and there's an umlaut on one of those, so I'm probably pronouncing it wrong. But typically they're time, and the label here is Mars orbital solar longitude. In other words, where it is in the orbit around the sun, all right? And so roughly 360 degrees in orbit, each degree is 2 days, because it's a 2-year year, versus geographic longitude. And this is thermal emission. This is sort of near the surface. And the idea is that if you look at a single longitude, you'll see a wave, and the tilt of these sort of gives you a sense of the propagation. In other words, if the waves were stationary, they would be sort of just perfectly horizontal. So anyway, Hofmöller plots are something that show up a lot. I realize it's not the clearest figure. There were two types of planetary waves. There was sort of the stationary waves, which, for example, in the Earth's troposphere are ultimately triggered by land-sea contrasts. In the winter, it's warmer over oceans than over land, and so that triggers a wave. Then there's sort of traveling waves, which are often more considered to be instabilities. And so I do have a pretty picture of a traveling wave, which we've gotten very interested in lately. This is from no gaps, and so it's the mesosphere, and it's water vapor. Okay? In parts per million by volume. So water vapor in the middle atmosphere is a trace constituent. This is near 80 kilometers, and this is for January. So this is summer, and we know that summer, there's water is the summer mesosphere is wet, is upwelling, makes it wet. Okay, so oscillations in the north-south wind will periodically cause that moist air to slosh northward and southward. And that's why you're seeing this wave 3 pattern. If I showed you this as a movie, you'd see these things moving to the left, which is westward propagation, because this is a Rossby wave. All right? So the period here and the speed of this propagation roughly gives you about a 2-day period. So this is not a fast-moving wave. It's about 2 days from one peak back to the second peak. This is the same thing now. This is the stratopause. Again, this is water. And you can see here at the equator where there's a nice gradient, again, north-south oscillations pulling in dry and wet air, north and south. Okay? So this is a fairly well-known phenomenon in the middle atmosphere, that you have these things. They tend to show up in summer, more so in the south than in the north for arcane reasons related to the middle atmospheric circulation. One thing that's gotten a lot of interest lately, though, and this is a paper that was sort of ignored for like 20 years, is that if you look at the ionosphere, all right, and this is a measure of the peak ionospheric density this is actually March, which is sort of an unusual time of year. To see these waves, you see that there's this 2-day oscillation in the peak ionospheric electron density. Moreover, when the oscillation kicks in, the overall density is lower. So the question then is, how can we link this mesospheric wave phenomena with the ionosphere? Well, we go back to the same kind of fundamental diagnostic that I've been talking about all along. we want to go back and look at what might the neutral composition be doing? What might the O to N2 be doing as a function of this wave activity? So on the left is my calculation from NOGAPS linked to the TIE-GCM showing meridional wave amplitude. On the right is a calculation from, it's just recently published, I'm going to say Cha Yue et al. And so the left calculation shows that from NOGAPS, we can take the 2-day wave and map it up into the lower thermosphere. And even in the tropics, there's a 2-day oscillation. Remember, that's where our vertical wind affected the entire ionosphere. And what he showed is that for periods when the 2-day wave is active, that this oscillation will tend to bring up more molecular nitrogen at the expense of atomic oxygen, and that's consistent with lowering the height of the electron density. So it's another example of a middle atmospheric phenomena linked to tropical upwelling and composition. So this is the same figure. This is from the NCAR, yeah, Yue and Wang, there's the reference. The NCAR time GCM, reducing the electron density for the same reason that KZZ did in our simple little 1D toy model. For stationary planetary waves, which I talked about land-sea contrast, probably the one that's upper atmospheric people have heard of, it's the most famous, is associated with stratospheric warmings. So in winter, the lower stratosphere gets very cold, and so the air just spins around. This is the polar vortex that all the weather people are making a big stink about this year. It's really a lower stratospheric, upper tropospheric phenomenon. But this circumpolar vortex will often be disturbed, and you can have a wave interact with the vortex. There are sort of two ways that can happen. This is a wave 1 displacement of the vortex, where it's shifted off the pole, and there's actually a little wave breaking here. Or you can have a wave 2, which is a split in the vortex. So wave 2 means if you went around a latitude circle, you'd see two peaks. Again, the middle atmosphere people have been all over this for decades, but it's only been in the last 5 years or so. Well, all right, so this is just more middle atmosphere with NOGAPS that really, extended the weather up to 95 kilometers. We looked at all sorts of effects on, for example, the temperature. When the planetary wave comes in, it's mixing in air from lower latitudes, which is warmer than this cold vortex. So the temperature at the pole goes up, and that's why it's called a warming. And at a certain altitude, it's really a decrease in the stratopause altitude. So we simulated a lot of this, the changes on wind, the planetary wave amplitudes. But this is a useful plot because in general, these stratospheric planetary waves that are causing the stratospheric polar vortex to change and the stratospheric warmings are generally thought to be filtered out before they get to the thermosphere. It really was thought to be a middle atmospheric phenomenon. So it was sort of surprising that during one of these warmings, they saw some pretty pronounced ionospheric effects. And so the question lately is how to explain that. This is data from Heliophysics. So it's the equator. It's not even the pole, it's the equator. And it's the vertical drift, which has a nice, well sort of understood diurnal variation. This is the control days. And then during the period of the warming, you see this diurnal variation is completely disrupted. Well, when we think diurnal variation, we should think tide. So we've got planetary wave, which is giving the stratospheric warming, affecting a tide in the tropics. And that's sort of where the cutting edges is trying to link those two. And this is not only neutral tide, this is the electrodynamic tide, so it's changing the dynamo. A year later, they looked at electron density, and they also saw some dramatic effects in the diurnal variation. So on the top is the total electron content for certain times of the day from a satellite data. And again, this is showing the Heliophysics Radar Observatory. And there's more of this peak in, let's see if I get this right. This is 10 local time, and this is 16 local time. This is the universal times are up there. So it's the local time of Heliophysics. So morning, afternoon. That's really what it is. There is more electron density in the afternoon under quiet conditions. During a big stratospheric warming, the afternoon electron density goes away, and we have more in the morning. So again, the diurnal variation in the ionosphere is completely perturbed. The bottom plot shows this vertical ion drift, which is, you see, for the day of the warming, completely different than climatology. So the models have been looking at this, and there are some ideas. They're getting some wave-tide interactions. There's this is Tim Fuller-Rowell, so what he shows is that this is the semi-diurnal tide amplitude decreasing during a warming. This is a terdiurnal tide, 3 per day. That seems to be dramatically increasing. Not every model gets this, but they get something. They get some tidal interactions with the warming. So that seems to be the area of nonlinear interactions between a planetary wave and a tide in the mesosphere, and then the tides can propagate up into the thermosphere, even if the planetary waves themselves can't. Yeah, they've done some intercomparisons, and everybody sort of has their own mode that seems to be enhanced. Seems to be how you handle some of the small-scale gravity waves, because that controls how what your winds are in the middle atmosphere, and it seems like that's the key thing for getting the right tidal mode to propagate. So this will give us a chance to turn to the last wave, which is gravity waves, which are the ones that really are the big uncertainty. These are vertically propagating waves where buoyancy is the restoring force. And, you know, if there's just a sort of a small conservative oscillation, that's not too exciting, but they grow with height, and as they get to a certain height, they get unstable, and they'll overturn. And you can just think of waves washing up on a beach. That's what transports. It crash against the wind flow and change the angular momentum budget. It can also transport constituents. These are too small to or too rapid to easily resolve. So this is where the residual KZZ parameterizations are all focused on. There were 3 sources. And these sources actually work on Mars as well. There is, this is this is just a map of, and it's units of like millipascal. It's a measure of gravity of the flux, of the vertical flux from small scale waves. And this is, I think, for July. So this is the Indian monsoon. So convection. Now, this is not latent heat release. This is mechanical. This is convection, cumulus towers slamming into the stable stratosphere and generating ripples that propagate up to the mesosphere. Mars has convection. Doesn't have latent heat release, but Mars has convection. There is topography. So the winter winds hitting the Andes, got to get over the Andes. And that triggers mountain waves that can propagate up. Recall that on Mars, the mountains are 3 times higher than on Earth. So you can see where gravity waves on Mars are going to be 3 times bigger, all else being equal, than Earth. And then, harder to see this, but shear in the, like baroclinic instabilities in the jet stream, which is something that governs a lot of tropospheric weather. And that also happens in the Martian atmosphere. So that's the source. The thing that's interesting is that these waves will grow. And one way to express that is to write the vertical flux of zonal momentum as due to these terms. Okay, so the idea is that this guy on the left is constant. This is the density. We know that goes down. Okay, so if this is going down, then these guys got to go up to compensate. This is the stability, the Brunt-Väisälä frequency to 0th order. We'll call that constant. This is the zonal wind and the phase speed of the wave. This could vary, and if this gets close to 0, because the wind is near the phase speed of the wave, then this amplitude goes way up, and that's where the wave will get filtered out. But all else being equal, if this goes down, the amplitude has to go up, so this variance increases as 1 over rho. So when we keep that 1 over rho thing in mind, because if you are measuring if you have a measure of gravity waves, that's what you want gravity wave variance from, what, let's say, density fluctuations or whatever it is, and you have it as a function of altitude, you want to look at that and see, is it increasing by 1 over rho? Because if it's not, then there's probably dissipation. And that's what they found on Mars. So this is the accelerometer data from Mars Odyssey. It's a paper by Fritz et al. This is density variances. So this is going from 100 to 140 kilometers. And if you look at this region here, the variance is increasing by about a factor of 5 or 10. But this is over about 5 scale heights. E to the minus 5 says it should have gone up by a factor of 150. So yeah, it went up, but it only went up by 1/30th of what it should. From that difference, Fritz et al. Inferred significant dissipation, and long story short, you compare that to Earth, you express that as sort of an acceleration, meters per second per day. Earth is somewhere between, depending on the sign, 100 is probably the max, and then there's a model on Mars, and it's like 300 to 600. So this then may be the reason that the homopause on Mars is higher than on the Earth, because the gravity wave fluxes on Mars are many times larger than on the Earth. And that's really coming back to, again, the large topography on Mars. So we can link the large topography, the gravity waves, to the homopause altitude, and that governs the thermospheric composition everywhere, as you've seen from our KZZ experiments. So I think that takes us full circle, where we really now have considered everything not everything, but we've got sort of at least a crude outline of a picture of ground to space coupling. We've looked at the 3 waves. They're all present on both planets, but the forcing is different. In general, the effects of gravity waves, I didn't get into it but tides as well, is greater on Mars, most likely due to the topography. Martian data is limited to the aerobraking, and we're going to get some composition of meteorological data, but the aerobraking can show us a lot. They can show us gravity wave variability, and they can show us tidal variability. There's some factors unique to each planet. So we can go back, and I hope we now have filled in, at least conceptually, some of these differences. We talked a lot about scale heights, okay? I didn't get into this explicitly, except for the fact that the dust storms really are in some sense related to the large eccentricity of the Martian orbit. We talked about the Coriolis. We talked about magnetic fields. We talked about heating efficiency. So I think we've covered pretty much all of these at some level. So what I'd like to leave you is some food for thought. Play God. To amuse yourself, because gods get bored. You're one of these like Greek gods who are always causing mischief, right? You decide to chop off half of the tops of all the big Martian volcanoes. What might that do to the Martian thermosphere, the Martian ionosphere, and to the spacecraft orbiting Mars? So I'll stop there. I didn't hear, so was there a question? Or you?
I was just hoping before, Dave,
aurora-generated sun. It just pulls from the aurora, these ripples, and those tend to propagate horizontally. They're called traveling ionospheric disturbances. They're sort of like gravity waves. But there's still a suggestion that so the terrestrial gravity waves break at the mesopause, which for the thermosphere is maybe enough because it changes the mixing and the homopause and all that. But then there's this thought that as they break, they re-radiate. It's secondary waves, and people have been modeling convection actually up into the thermosphere, but it's like a secondary effect. It's like a two-step process. So then there's the question, and some people say, are these secondary waves, they break, are they important for thermospheric momentum and all that? One of the issues with the thermosphere is very viscous, and so there's this thought that these waves should damp out quickly just because it's like, trying to oscillate like a jar of pudding, it just doesn't propagate very far. But I think there's some observations from Airglow showing that there's some. So it's not purely a middle atmospheric phenomenon.
Call the mountains or leaders.
Yeah, with my hearing, so someone's going to have to repeat that.
How tall are the mountains on Venus?
No, I have no idea. I know they observed active Fran.
They're not as high as Olympus Mons. You know the number, David? Probably have.
Venus is smoother than Mars.
It's smooth. It's very smooth, and in fact, the mountains are. There's just a few mountains. I mean, they are pretty high. Maxwell Montes is pretty big. And I have a feeling Maxwell Montes may be higher than Everest, on the back, but most of the plains is very flat.
Yeah, I mean, I did the fun statistic that I always saw was Olympus Mons.
What is it?
Yeah, Olympus Mons is the highest volcano in the solar system, and that was the stat that I ran into someplace with the fun fact on Wikipedia. Gotta be true, I read it on the internet.
The internet was right.
But the interesting thing about Venus, of course, is you have solar tides, gravitational solar tides. So, even though